Hey, welcome back everyone. In this video, we're going to cover the basic concepts in fuzzing. I want to give you an idea of really fundamentally what a fuzzer is, and really, if you think about it, hey everybody, welcome back. In this set of slides, I want to give you the basic concepts behind really any fuzzer, and to talk about how fuzzing technology has evolved as we go through those concepts. So I want to start out by saying there's a really simplified view of application semantics that we use in testing. And that's, there's some sort of app on disk, but we're going to run it. And as part of running, there's a process created. And that application will read in some input. Now, examples of input are from a file, from the network, from mouse clicks. It could be a combination of these things. But after that input is read, it's going to be processed. Now, the reason I like this view is because when you think about testing in general, what a tester does is they come up with an input and then they observe how it's processed, and often will look for example, for correctness, for invariance. Now, if you're a pen tester, you're trying to create an input that violates an invariant and triggers or exploits the bug. Well, if you're a developer, typically you're trying to create a set of inputs, and then what you observe or test for is that you're getting expected behavior. What a fuzzer is trying to do is really replace the human. And so a fuzzer has at least two algorithms. The first algorithm, the input generation algorithm, is going to automatically come up with inputs to give to the program. The second algorithm is what I call an oracle. And the job of the oracle is to monitor execution, decide whether the program has gone wrong or not. And at a high level, if a program reads an input and it never goes wrong, we say the input is good, else we say it's bad. So if we look at the input generation algorithm, there's really a wide variety of things you can do. You can do something as simple as use a random or even a fixed input. You could enumerate from a grammar of what you think inputs would look like. For example, if your application reads from XML, you could write a grammar for XML and enumerate that grammar to test your application. You could mutate known inputs. For example, if you have an application that processes MP3 files, you could start with an example MP3 and keep mutating it until you find, for example, bugs. Or where research has been heading a lot in academia is using something called symbolic execution, where we actually analyze the application as it's running, build up a formal model of it running, and use that to generate inputs. When we look at oracles, there's a wide variety of oracles, and often you look at what sort of expense those oracles have. A typical oracle you may see is a definition of a program going wrong is it raises a signal, such as a sig-sig-v, a sig-bus, an assert failure, and so on. The nice thing about these sorts of signals is they're relatively easy to detect, so your security oracle doesn't have to be complicated. Now, for fuzzers at the application layer, suppose you're fuzzing a web app, you could look at application responses. Is it returning an invalid HTTP code? Does it hang? And so on. You can also go even deeper into execution introspection. We see some of that with some fuzzers, for example, with Libfuzzer. And Mayhem also does this, where you're actually monitoring deeply every step of the execution. You can find really interesting bugs, such as the program used a variable without defining it first. And so there's a wide number of input generation algorithms, security oracles. What fuzzing is about is making choices, trying to find the right balance so that you can automatically test the application and find interesting bugs. Now, as you get more advanced, you're also going to add more algorithms. For example, how you create this process is actually an area of research. When you look at fuzzing, you want to be able to create this execution cycle very, very fast. And so initially fuzzers used, for example, the Unix fork process, which is pretty expensive. Where we see fuzzing going is using less expensive or primitives. For example, Libfuzzer, as we'll go over, uses in-memory fuzzing, which is faster than just launching the process with Unix fork. All the way up to some research, for example, by Brund and Falk, who's using VMs. And once the process is created, he's using VMs to roll back. So this process of launching the application or launching it for the intent of fuzzing is very fast. Now, another example algorithm you'll commonly find are corpus management. As we said, the fuzzer generates inputs, and as we fuzz, we can collect those inputs to come up with a test suite. The test suite is the representative set of inputs for triggering all observed behaviors as you're fuzzing. So there's a lot of design space considerations, and we'll look at a few examples in just a minute. But one of the primary considerations that we look at is how do I intelligently generate inputs? And here you have a lot of choices as we just talked about. What sort of bugs do you want to detect, and at what expense? You can often get better bug detection by building in more expensive instrumentation, but then that cycle of rapidly fuzzing gets slowed down, so there's a trade-off. How fast is the runner? And as I mentioned, you can just simply launch the process, or you can launch the process and then use fancy checkpoint backup restore mechanisms to make this process even faster. Does the algorithm scale to increase compute? This is one where we're seeing a lot of increased research because the existing fuzzers are typically designed to run on a single host, and there's not a lot of research of, suppose you want to run it on 100 different hosts in parallel. So how do you maximize your return? We're really in the era right now of just using plain brute force parallelism, not a lot of intelligence behind it. Fifth is, who is the target user and what is their skill level? I can tell you when I was doing research and when I was looking at the Cyber Grand Challenge, we were looking at the most advanced algorithms to find the deepest bugs. But what we found actually is that when you go and you're looking at adopting fuzzing, the biggest barrier to adopting a security technique is the user will have a low skill level. Now, I don't mean they're dumb, I mean they just never fuzzed before. Similar to having a low skill level is they're just not that interested in putting a lot of work into something until they see return. If I came to you with a killer software analysis technique that required you doing a lot of work, you'd probably be a little bit skeptical unless I could show you that that investment would pay off. And so what we see in research is we want to have fuzzing approaches that as a user puts in more effort, they get better and better results, but they can put in very little effort to at least get something. What languages am I targeting? A lot of the fuzzing work, and when you look throughout history, was targeting Unix applications that were processing binary data. They were looking at MP3 files. They were looking at PNGs. Things change when you start looking, for example, at interpreted languages that are responsible for processing text. Simply speaking, when you want to fuzz Python, it's going to be quite different than when you want to fuzz a C or Go or Rust application. And so on and so on and so on. And so these are design space considerations when you're looking at those fundamental algorithms, and they'll give you different trade-offs. So if we look back through computer, the term fuzzing is actually one that happened around the 1980s, but if we go back, fuzzing is really an area of research that has a long history in what's called randomized testing. And I found this great blog post from Gerald Weinberg that I'll read it to you here. It's really interesting. We didn't call it fuzzing back in the 1950s, he says, but it was our standard practice to test programs by inputting decks of punch cards taken from the trash. We also used decks of random number punch cards. We weren't networked in those days, so we weren't much worried about security, but our random trash decks often turned up undesirable behavior. Every programmer I knew, and there weren't many of us back then, so I knew a great proportion of them, used the trash deck technique. So this idea of using random inputs goes back to the 1950s, and it's actually still effective today. Now the term fuzzing, what we're talking about today, was actually coined around 1988. It was really just a relabeling of randomized testing, where Bart Miller and some students did some experiments. And in those experiments, they showed they could crash between 25 and 33% of all Unix utilities by providing them a random input. Now this idea of a dumb fuzzer may seem, well, dumb to you. And it's pretty simple to implement. The nice thing about it is it's pretty simple to implement. You can just launch a process in a shell script by repeatedly causing fork. You can generate random input, and you can see if the program crashes. The cool thing about this is actually really simple to use, and you can check an application with no developer participation or no modification, which means you can start taking advantage of the law of large numbers. You can start checking a large number of apps, not very deeply, but you can check them for basic errors. For example, in 2014, I was having a discussion with a PPP member PPP is a CMU hacking team, and this guy was a really elite hacker. And he was like, yeah, you know, there's not easy to find bugs under well-tested Unix utilities. And so I wrote this little script, and as part of this bet, I actually found 52 new bugs in 29 programs. And all this program does is print 8,000 A's, and then it brute forces command line options because I don't know what's going to be reading, and it runs the program for up to 1 second. So this 6-line script found 52 bugs, a very dumb fuzzer. Now what's surprising me is finding simple techniques like this actually working for a lot of legacy software. When you look at things like airplanes, ships, IoT devices, these things were not written with security in mind. So these sort of simple techniques often pay off. So I call this random input or mutation the generation 1 fuzzers. Now what we saw after generation 1 is people said that random input generation is not very efficient. Let's start looking at defining protocols or grammars or models of what the input should look like so that we don't waste time. And this led to a host of research and a host of tools such as Peach, and really the first commercially viable product at the time called Code Intelligence, now called Defensics, where you defined a protocol, for example, for ARP or for TCP, and the fuzzer was just iterating over that protocol. What we've seen in generation 3, and one of the reasons we're seeing people like Google and Microsoft and others start to take up fuzzing as really their primary software security, is the idea of using application coverage in your fuzzer. And I'll talk about that more in a second, but the main idea is as you fuzz, you can learn about what code's been reached and then use that information to try to target new code. If you think about it, if for some reason you could test every possible input a program would accept, then some subset of that is the inputs that trigger bugs. And so if you can increase coverage, you're kind of going along this idea of, hey, let's be a little bit smarter about trying to get new behaviors out and seeing if they're bugging. All the way up to symbolic execution, which is, as I mentioned, taking formal methods and applying it to this problem of how do we intelligently generate inputs. So let's dig into these a little bit deeper. So one of the fuzzers that really sticks out in the history of fuzzing and is still used widely today is AFL. AFL was created by Michael Zawiski. It was first released in 2013. And the really awesome thing about this fuzzer is Michael did a lot of work on real programs to make A, the fuzzer really easy to use, but B, he used a lot of heuristics and then tested them over a large data set to find out what works and what didn't work. Now, at a high level, he had a very simple runner. He was using Unix fork. We'll talk about that in a second because that's one of the places Libfuzzer advances on AFL. He used a number of heuristics for generating inputs. In fact, the cool thing about his fuzzer is he has different stages. So he has some well-known patterns that he might use at the first few phases and at the end use random. And that way you're trying to check the common things that people get wrong again and again and again first, and if those fail, later on you start checking random. Now, the oracle used was very simple, just Unix signal. In fact, at some level, AFL isn't detecting bugs, it's simply detecting when an application raises a Unix signal. The real technical advance, if you want to dig deep into AFL, beyond the heuristics, was AFL was really the first fuzzer that was doing active corpus management. It was taking the set of inputs that had been generated by each fuzzing run and managing them and doing things like test case minimization and corpus culling with min setting. So what is test case minimization? Well, if you're going to run an application on an input, often the length of that input determines how long it takes to process. If we go back to an MP3 player, a big MP3 is going to take a long time to process and a small MP3 is going to take less time to process. And so AFL has built-in logic to try to minimize test cases because you'll get a higher throughput by exec count. You can run this process of creating a process, giving it an input, processing it, seeing if it crashed or not, and then going back to step one again and again and again much faster. The second thing he did is he actively managed a corpus, and that corpus represented the coverage he was getting in the application. And so what he was trying to do, if you think about it, was he was trying to say, hey, here's a set of inputs that give me a certain coverage, let's try to grow it. So let's talk about coverage a little bit more. Here's a very simple example that we talked about in a previous lecture where it reads in an input, and if the input is BUG, there's a crash. And so you can think of any program as first in text form, but also in a graph. Often we'll call these control flow graphs for a single function. We'll call them call graphs between function, program dependency graphs in the entire program. So you can think of this graph here. We have statements 1, 2, 3, 4, and 6. And when we execute statement 1, just the function prologue, statement 2 is always called, but 2, it can either go to statement 3 or statement 6. And 2 can go to 3, can go to 6 or 4, and then 4 is crash. It's a bad state. So formally, we can think of a program really as a graph, VE, where every vertex is a node, or I'm sorry, every node is a statement in the program. And there is an edge if there's a possible control transfer between S1 and S2. Now, a longer version of this course, I'll talk about actually creating a control flow graph is not so straightforward because they're both over and under approximations of the program. But if you've dealt with programming for any length of time, you kind of get a rough idea of what a control flow graph would look like. So the idea in coverage-based fuzzing is we want to create a test suite that has coverage. So if we think of this example, the test suite mom, Bob, bar, and bad achieve 100% branch coverage. If we think of this as a graph where we have a true and false branch, you're exercising each true and false branch with that test branch. On the other hand, if you have a test set mom, dad, Bill, sad, lol, all test the same code. You're not increasing coverage. And so it would be wasteful to test the application on all 5. What AFL did, and coverage-based fuzzers like AFL, is they use coverage information to call the test suite, significantly improving fuzzer efficiency. They keep a set of inputs, which they call the min set, which represent the minimum set of test cases that trigger all observed behaviors, and they fuzz based on those. They're doing mutation-based fuzzing based on those to try to uncover new coverage. Now, there's a funny story here actually in AFL. AFL is doing what they call min setting, but it's actually not using the real minimal set cover algorithm. And so kind of a fun research project, if you're up to it, is to actually put in the actual minimum set cover algorithm. And what you should see is AFL becomes actually more effective, though at potentially the cost of running this min set algorithm. Now, in my experiments, it's worth it, but it's kind of an interesting thing when you look at these sorts of trade-offs developers make. So AFL calls in particular based upon edge coverage. Now, that's not the only thing that you could call on. When you look at testing literature, there's a number of different coverages out there. There's function coverage. Do you have at least a test case that covers each function or executes each function? Statement coverage or node coverage. Do you have an input that executes each node? Edge coverage, which is AFL, which is you look at the edges and you want to cover those average. All the way down to, some people will talk about path coverage. Now, I want to spend a moment here talking about path coverage. If you look at examples 1 through 3, you can calculate the percentage of a program covered. You can say how many nodes there are and what percentage of nodes you're able to test. The problem with path coverage is there's an infinite number of paths in the program. And so you really have no idea percentage that you've already tested. And in some ways it can be misleading. People will often think of programs as this directed acyclic graph, but they forget their cycles. And the number of times you execute a cycle can matter. After all, a basic buffer overflow on string copy is really determined by how many times you execute that copy of characters, that loop in the program. So people will talk about path coverage, but it's a really hard thing to ever optimize for because it's easy to get new path coverage. You just execute a loop another time, but that doesn't mean you're executing any sort of new behavior. So AFL, Libfuzzer, and really much the current consensus is that edge coverage is really where it's at. So I want to do a quick AFL walkthrough. And what I have here is I have that small program I just talked about, test me, BUG. And when you get bug, it will crash because in this case, there's undefined behavior. There's a 1 divided by 0. So AFL is intended for developers. So what you do is in your make file, you compile using AFL GCC. Now here I've hard-coded in, that's the compiler. When you're trying to build something from source, often you can use the CC AFL GCC to set the CC environment variable because modern makefiles often use the environment variable to compile. So when you compile with AFL, what it does is it instruments the code to collect that coverage information. After instruments, you can run AFL, and I'll just show you the run script here. The way you run AFL is you have an input corpus. This is the set of initial test cases you have, and the easiest thing to do here, if you have no example initial test cases, is to steal one from the application or even just have a bunch of A's. Here, I have a good test case. So a good test case is just the word bar. It's not going to trigger bug. It's not bug, but it exercises the code. So when you run AFL, it's going to output its test cases that it produces in the out directory. And it'll give you this nice UI showing progress. Again, this is one of the advances. Michael made this super easy to use. And so you can see here we're running, it's keeping track of your execution speed. And here in the small program, we're getting over 1,000 executions per second, almost 2,000. It keeps track of the total paths, its unique crashes, and then it's keeping track of edge coverage. And it gives you some more statistics. And I invite you to read through the AFL documentation if you want to get deeper. Now, when it runs, when it finds a crash, as I mentioned, it stores it in the out directory. And it stores it in the out directory. You can actually look at them, at least in this as text files. For example, it found bug. Now, AFL will run indefinitely, and it will output, if there's multiple ways to reach the same bug, it will output them. So if we continue to run AFL, it would potentially find other ways to reach that exact same bug, perhaps by not having a new line or something to that effect. So AFL is super easy to use. You just have to change the command line of your compiler. The actual instrumentation it's adding is very simple and unlikely to affect your application in any way. And then it's really simple to run. You provide an input corpus in an in directory and outputs in an out directory. So AFL on the design decision decided to detect bugs that raise a Unix signal. And that's why AFL has been so successful in finding things like buffer overflows, because those by definition will just raise a Unix signal the first time you trigger them. The algorithmic efficiency, really what we've learned since AFL has been released is it's been limited by 4. In fact, the fastest people have really gotten is up to about 20K per second. This is according to Brandon Falk. And we've also seen research papers written that show that the overall scalability of this, even on a single computer, is limited by the Linux kernel. In fact, if you try to parallelize this too much on a single Linux system, you'll actually see decreased performance as you add cores. The target user and skill level, well, Michael made it incredibly easy to set up, and that's why it became popular, and that's why it had such a profound effect. Now, as you get deeper with AFL, you can write fuzzing harnesses. A fuzzing harness is something like a test suite harness, which targets the code that you actually care about testing. So the languages supported, well, it originally was looking at C, but today many compiled languages support AFL. You can go and you can look at, for example, OCaml, a functional programming language, and it supports AFL. Now, it doesn't support, for example, application state. What it's doing is it's doing a memory set on each invocation. So for example, file state is not handled. This means you can't use AFL, for example, to fuzz an application where that application first writes out a PID file, and if that PID file exists, it doesn't go further because it won't remove that PID file on each invocation. Now, AFL is intended to analyze a single executable at a time. You can't use AFL to analyze, for example, a system assistant, SOS as I put it. And so when you start thinking about where is AFL's sweet spot, it's really breaking down a monolithic application like you may see out there where you have a web server running Python, which is a microservice writing to a database. You would decompose that in the set of executables and run AFL on each one individually. So after AFL came a new fuzzer called Libfuzzer. Now, Libfuzzer is part of the LLVM project. So to use Libfuzzer, you have to be using the Clang compiler. The big difference between Libfuzzer and AFL, well, there's many, but there's two main ones. First is Libfuzzer decided to be an in-memory fuzzer. So it's not really based on this idea of fork and exec. Its idea is that it's going to reset the memory state each time it does a fuzzing, it processes a new input. Now, this introduces, of course, some limitations on what sort of parts of the application it can analyze, but what it gets is it's exceedingly fast, often much faster than AFL. Now the oracles are also different. When you look at Libfuzzer, its oracles are based upon compiled in sanitizers or compiled in instrumentation. AFL, as I mentioned, is really based upon Unix signals, signal abort, while here we can compile in more fine-grained instrumentation. So sanitizers, they get compiled in, well, there's one called sanitizer coverage, which instruments the application to include coverage. But then the most popular is, for actually detecting bugs, is address sanitizer, also called ASAN. Now, ASAN is a fast memory error detector for things like out-of-bound heap, stack, and global accesses, use after free, use after return, use after scope, double free, invalid threes, kind of what you would think of as your classic memory safety problems. But you can also use other sanitizers, such as undefined behavior sanitizer, which is a fast detector for things like using misaligned or null pointers or signed integer overflow, or as a division by zero, which is really undefined behavior in the standard, or conversion to or between floating point types. And so by compiling in different sanitizers, you can find different types of bugs, often at a finer granularity than AFL. So let's talk about Libfuzzer. So I have Libfuzzer here as well. And so if we look at this test me app, I've modified it so that it takes in a buffer and a length. And I'll show why not in a while. But one of the cool things that you can start detecting with Libfuzzer is things like potentially uninitialized variables. And so here I have an uninitialized variable where OK is never initialized. Now, the way that you use Libfuzzer is a little bit more complicated, quite honestly, than AFL. You have to always write a harness. And the way you write a harness is you write this function called LVM fuzzer test1 input. When people were designing Libfuzzer, they tried to think of, well, what's the most general abstraction of an input? Well, to them, the most general abstraction was a sequence of bytes. And then it's up to the person writing this function to say how those bytes should be represented as meaningful data in the application. Well, in our case here, because this is so simple, we can just pass it directly to test me because we're taking in a buffer with a length. Where a lot of the really cool advances for LLVM come in is when you have more extensive data types. For example, with LLVM, you can handle fuzzing compressed files because, for example, this can take in the input and then uncompress it or compress it and then feed it to the application depending on what it is intended. You can add things like checksums and so on and so forth as needed. And so it really is much more developer focused. It's more for the actual developer using it. While AFL can be used by the developer, you can do all this harnessing, but it also works for the security practitioner who has less ability to modify the source. So the bugs detected are compiled in sanitizers. They took a different design decision than AFL, and in fact, they can detect more issues. But the expense they have is that they have to be compiled in, and you have to be using the Clang compiler. If you've read any papers in application security, one of the ones I really recommend is from Dawson Engler. It's called Billions of Lines of Code Later. And what they found when they founded this company called Verity, a static analysis company, is they were doing all their experiments in GCC and finding great bugs. It was working great, and they commercialized it. Some of the first customers they went to were like using the Borland compiler or a different compiler. And that was one of their huge challenges was in commercializing, is handling all those different build environments that users may have. So Libfuzzer is very opinionated. Use Clang. You just have to use it. So that's something where you get a benefit as far as security, but it also can limit its general applicability. The algorithmic efficiency, well, it's not limited by fork, and so often it's going to be faster. Now, in exchange for this, you often have to be much more careful with Libfuzzer that you're not using up all memory. Like if you have a memory leak, you could potentially use up all memory in Libfuzzer, while AFL, it's resetting the actual process on each execution with fork and exec. For compute scalability, again, parallelism isn't designed in. What they were really looking for was a little bit deeper bugs and faster execution. And the target skill level is really for the developer. And so when you're trying to fuzz these, you have to go in and really understand the source code. The languages supported are mini compiled languages. Interpreted languages are out of scope, just like AFL. And the application state, the fuzz harness, again, must be very careful. Libfuzzer is similarly designed for a single application. In fact, this is a theme you'll see. I don't know of any system of system fuzzers out there. If you're looking for a PhD research topic, that may be one of them. So finally, I want to talk about generation 4 and talk about where some of the fuzzing research goes. And I want to talk about this in terms of Mayhem, the project that we had at Cyber Grand Challenge, and also commercializing it, as well as, for example, Driller, which is by some ASU professors. Jan and Fish were part of Anger, the research project. And I want to talk about the direction they're going. And what they're doing is they're taking this idea of traditional fuzzers like AFL and pairing it with symbolic execution where you're using formal methods to generate the inputs. So I want to show you what Mayhem does. So Mayhem is actually a container-based fuzzer, meaning Mayhem is really intended to take as input a container, and it's going to execute an app within the container. And one of the things Mayhem can do is it can handle application state. So if an application writes a file during a test run, Mayhem will undo that write when it goes to do the second test run. And so I have here the Mayhem UI on demo.forallsecure.com. And what you do for Mayhem is you just have to write a Mayhem file. So Mayhem will work with binary applications that read from file inputs, standard in, as well as the network with no modifications. Handling network inputs is an advance over AFL and Libfuzzer, and it was put in there really just to make things easier for the user. So you have to specify in Mayhem the Docker image and then how to execute the application itself. Then you type Mayhem Run. And what Mayhem Run does is it's a distributed platform, so it does it all in the cloud. It's going to take that image and it's going to start looking at how do we scale this within the cloud itself. Now, it'll take a second here for the run actually to show up, but here we go. So Mayhem does a couple of different analysis. One of the things it does is it takes an input corpus if you provide it and does a regression test, and then it starts doing this fuzzing, or what we call in the UI behavior testing. And so when it's doing behavior testing, it's executing that application, and in this case, it's executing it, starts out 16 runs a second, but it's about 1700 runs a second in the steady state. It's executing that full Docker image and resetting that Docker image at that rate. And just like AFL or Libfuzzer, it's looking for things that are raising a Unix signal. And when it detects those, it logs it and it keeps the input. Now, one of the things Mayhem is also intended to do is help you grow that test suite. And so you see Mayhem keeps going. Libfuzzer, for example, typically stops after the first crash to grow that test suite, trying to get new coverage. Now, Mayhem is using fuzzing plus symbolic execution to do this. We're also doing deeper introspection. So for example, Mayhem with just the binary can detect an out of bounds read that's not raising a Unix signal, because we're actually, when we produce a test case that gets new coverage, we're running a more full analysis looking at each step of the execution for something that's violating the ABI. Now, just like other fuzzers, when there is a problem, you can actually just download the test case. Download the test case that triggers the behavior. So for example, if we look at this one, the input validation, this is triggering a buffer overflow in how this particular application, Lighty, a web server, handles input, and you can download it and actually just look at it. So Mayhem generated this input here using a mix of symbolic execution and fuzzing. And it's kind of interesting. This is a very simple input, but it's this pound sign, this processing that would crash Lighty. And if you go and look, Lighty is used on embedded devices. It's used in IoT devices. It's used in high-performance web servers where people want a low memory footprint. And it's even used in cyber-physical systems. So that's looking at generation 4, where you're trying to advance beyond just command line. You're going to inline it with the compiler. Can you take in the entire binary? Can you deep introspection? How do you make it easier? So when you think about the science of fuzzing and fuzzing 101, fuzzing is about replacing manually testing with algorithms, with things like the generation algorithm, the detection oracle, and the runner. and doing things like corpus culling to help manage how to be effective at finding new inputs so that you can find new interesting behaviors and ultimately bugs. The popular industry fuzzers that people are using today are things like AFL and Libfuzzer, which are completely open source, or when you look at commercial solutions such as ours, we can handle things like binaries. But fuzzing research continues to be ongoing. One of the things that we found as we've gone to market is there's actually very little research in how do you fuzz interpreted languages. If you write a Python app, you're not dealing with bit vectors, you're dealing with real numbers. You're dealing with string processing primarily and string processing bugs. And this is something that fuzzers typically today don't handle that well, so it's an active research area. How do you scale across distributed CPU resources is also an interesting question, as well as things like, hey, how do you optimize a portfolio of fuzzers to get the best effect? In fact, when you look at the Driller paper or Mayhem, really what we're doing is we're trying to optimize symbolic execution, one type of what some people call a fuzzer, with a more traditional instrumentation-based fuzzer.